Hello and welcome to this electrodynamic series. Today I will start the volume integral. A volume integral uh, of a scalar t or a scalar function t can be given as this t times d tau. Well, d tau is the volume element, right? In a three-dimensional space, for the Cartesian coordinate, it will be equal to dx dy times dz. Okay. If we have space more than 3 dimensions, then that quantity is no longer a scalar quantity, right? And that quantity will be a vector quantity. So what how can we write? Okay, so t is a function of x, y and z, right? So it's written as x, y and z, and this d tau is just dx, dy and dz. And of course this is the triple integration, right? Because we are using the volume element. Okay, so and we will put the limits of x, y and z, upper and lower limit both. Now, so suppose what is its physical implementation? uh, so we have this let's say let's say we have this distribution of mass, right? And of course that distribution may not be a uniform distribution, so some at some point of this distribution may uh, have more number of masses, okay, and some may have very low number of masses. So we can just define this distribution through a function, let's say rho, which is a function of x, y and z. So rho is here the mass density of that distribution, right? And if we think that t instead of this rho, okay, uh, I'm sorry, if we replace this t by this rho and take the d tau as it is, then so this term will give the total mass of that distribution. Okay, how is it how is it is going to be? We know that this mass is density times the volume, right? So and it is exactly the same thing. Mass is equal to density, so we have this density times the volume, and we are integrating over all the space, so we'll get the total mass of the distribution. And yes, in the similar way, instead of this mass density, we can have this charge density. Okay, so instead of getting the total mass of the distribution, we can get the total charge of distribution, and this is gonna be used in the electrostatic. Similarly, we can have the current density, right? So in that case we can have we can have this the total current distribution. Although the current, in the case of the current, we do not use this volume integral, we use the surface integral. By the way, we will see this. Okay, so let's forget this current density for now. Okay, and one more thing, that we are taking the scalar quantity over here. We can also have this let's say this vector, okay, volume integral of this vector field v. So we can obviously expand this vx d tau plus vy d tau plus vz d tau, and we have this this triple integral, right? and so this will give a scalar quantity, but this will give a vector quantity, right? So yes, here in this case this V may be a current, right? It may be a current distribution, right? It may be a current density, I should say. Okay, and this current density times this volume integral will give the total current that is available for different directions. Okay, one thing that I should add this x cap, y cap, and this z cap direction. So this volume integral will give the total current along the x direction, y direction, z direction. Okay, so we can in summary I can say that we can write this volume integral either in the form of a scalar variable or a scalar field, or we can write it in the form of this vector field.